Good afternoon, ladies and gentlemen. I'm Peter Goddard, Director of the Institute for Advanced Study. It's my pleasure to welcome you here this afternoon to this Institute lecture. Our speaker today is Matias Zaldarriaga. Matias has been a professor in the School of Natural Sciences since last July. At the end of his lecture, he will be very happy to take some questions, and then we can continue the discussion after the end of the questions at a reception in Ford Hall, to which you're all invited. Matias has made many very important contributions to our understanding of the early universe and to the relationship between particle physics and astrophysics and cosmology. He developed techniques for improving greatly our ability to calculate the properties of the small fluctuations of the cosmic microwave background, which tell us about the beginnings of our universe. Matias obtained his first degree from the University of Buenos Aires in 1994 and his doctorate from MIT in 1998. He was a member of the Institute from 1998 to 2002, as well as being an assistant professor at New York University from 2001 to 2002, when he joined the faculty of Harvard University as an associate professor. In 2004, he became professor of astronomy and physics at Harvard, before moving to the Institute earlier this year. Matias's work has gained him many prizes and honors, including a Sloan Fellowship in 2004, the Greboff Medal of the European Physical Society in 2005, and a MacArthur Fellowship in 2006. Today, Matias's title is In the Beginning, Modern Cosmology and the Origin of the Universe.
Thanks very much, Peter. The goal of the talk today will be to tell you about modern cosmology and try to tell you the story of how we understand how the universe came to be, how we understand it today, and try to get to some of the questions that we ask about the very beginnings of our universe. Now, if we want to talk about modern cosmology, our modern view of the universe and how different things that we observe in the universe came to be, what we are really talking about is the theory of the Big Bang, or the Big Bang model of our universe. So what I want to do is to start by telling you about the Big Bang model, which is very, very well established. And at some level, the Big Bang model is a little bit of a misnomer. And I want to tell you a little bit about that. So, of course, the question of how the universe began, or what is our universe, what do I really mean by the beginning of our universe? So all of these questions, one could spend a lot of time discussing them, and even where to start is not clear. So I will start fairly recently in the development of our ideas about our universe, just so that I can get to the end faster, okay, to what we really think today. So, of course, there's a lot of previous work that led to where it'll be my starting point that I will not talk about. So I'll start with Edwin Hubble, an American astronomer working in California in Kitt Peak Observatory in the 20s and 30s. He made two important discoveries for our talk today. One of them was that he established the fact that what were called nebulae, or at least some of the things that were called nebulae in the sky, which were nebulae stands for cloud, so things in the sky that were not stars, were indeed other galaxies very far away. And the other thing that he discovered was that those galaxies were moving away from us at pretty high velocities, and with a velocity that was faster the further away this galaxy was. So let's talk a little bit about what Hubble, or give you a rough sense of what he did. So for that, let me talk to you a little bit about spectra. So if you take light and you send it through a prism or some device that does the same thing, it would split it into colors, and those colors, color constituents of light is what's called the spectra, so they go from the red to the blue. It turns out that if light is going through some cloud of material, say some cloud of gas, and you pass the light that comes, say, from a star, comes through some cloud of gas, you pass it through this prism, and you look at this spectra, you look at the colors, you notice that there are certain colors that are missing. What happens is that various elements, like hydrogen, carbon, whatever element you like, absorbs lights, or actually also can emit light, but it does it in a specific set of colors. So if you look at this cloud of gas from very far away, you can tell what it's made of by looking at what are the colors that are missing. Okay? So this is how astronomers are able to determine the composition of faraway things. So they compare the missing colors, or these are called absorption lights if they're missing, or if the gas actually emits those colors are called emission lines. They compare those lines to the same spectra, the same lines that are measured in the laboratory for hydrogen or carbon or whatever you like. And so that's how, by matching those, it's kind of a fingerprint, and you can tell what the thing is made of. So that's how we know composition of stars or various things. There's the other piece that you need to understand what Hubble did is what's called the Doppler effect. And we are familiar with this in the case of sound waves. So if you see some train or coming to you, or a car, you notice that the sound it makes changes depending on whether the car is coming towards you, or it then goes in the past you hear something, a room, the pitch of the sound is changing. Same thing happens with light. If the source of light is moving relative to you, the whole colors of light are shifted, are moved in this spectra. And if the thing is moving away from you, the colors are shifted towards the red. So all of these lines would move towards the red side of the spectrum relative to the ones in the laboratory. And that's called a red shift, the red shift. And if the object is moving towards you, however, the lines are slightly shifted to the other direction, to the blue. This is exactly the same as with sound, but with light. And what Hubble discovered is that if he took spectra of these galaxies that were far away from us, the location of these lines were all shifted relative to the laboratory. So these objects were moving with respect to us. But he also noticed that objects that were further apart were moving faster. So by seeing how much these lines are shifted, you can also tell how fast the thing is moving. So just as with the case of the sound, the faster the thing goes, the bigger the effect. So he looked at spectra of stars and galaxies, and this is just a sketch, right? A star, a galaxy which is made of many stars, a further away galaxy that looks smaller, and even further away galaxy that looks even smaller. And he looked at the spectral lines in the colors, and they are all shifted towards the red, indicating that things are moving away from us, and the further away they are, the faster they are moving away from us. And that's what we refer to as the expansion of the universe. Basically, more distant objects are moving away from us with even larger velocities. And he measured the velocity. So this is from the original paper by Hubble. The y-axis is the velocity that he measured using this redshift. This is his estimate for the distance to the various objects, and each point for one object. And so there's kind of a trend in which further away things are moving faster. This is just same thing, but a modern version, just to say that this is not all based on some old data like this, right? So we now can do it much, much better than Hubble could. The important point is that what he discovered was that this velocity with which something is moving away from us increases when for things that are further away, in a way that it's proportional, meaning if something is twice as far away, it's moving twice as fast. If it's 3 times further away, it moves 3 times as fast, and so on. Why is that important? Because if you imagine now asking where those things were in the past, you'll discover that because of this proportionality, everything will end up in the same at some point in time in the past, everything will end up in the same spot. Why? Because even though something might be faster, so you would think it takes more time to get to where I am if I go backwards, it is moving faster. So it exactly compensates the increase of the distance of the thing that's further away. It's exactly compensated by the faster that it's going. So this means that this expansion of the universe, this fact, and by that I just mean that things that are further away move away from us proportional to how far they are, so twice as fast if they are twice as far, means that if you trace them back, we were all together at the same spot in some sense, although this might not be the best of analogies, but in the way we think about it. But in any case, for the purpose of the talk, let me say like this. We would all end in the same spot at some moment of time, and that moment of time is what we would call the Big Bang. Okay? So in some sense, we live in the aftermath of this Big Bang. So for whatever reason, I don't know, everything is moving from this initial point in time, everything is moving away from each other with sometimes very far away things with great velocities. And we live in a universe which is the aftermath of this thing, this explosion. In some sense, rather than call it the Big Bang theory, most of what we do in cosmology is study the aftermath of this Big Bang. So it's not so much a theory of the bang itself, at least for the beginning of the talk, but a theory of what happened after this bang. And this was nicely put by Alan Guth, who will come, a physicist at MIT, who will resurface later in the talk. He said the Big Bang theory, what usually is called the Big Bang theory, is not really a theory of the bang, but it's just a theory of what happened after the bang. Okay? So this observation that the universe it's expanding, or that things are moving away from each other with a velocity proportional to the distance, immediately implies, when you go back, that there is this kind of beginning, this initial time. And we are kind of living in the aftermath of this bang, whatever that is. But this fact that we live in a universe that in some sense had a beginning and that it has been changing, it also, I mean, the fact that it's expanding, it means it's changing with time. The distance to your next neighbor is increasing as you go forward in time, and also it means that average temperature of the universe is decreasing. This is no longer just a logical conclusion of the fact that we see this expansion. This is an observational fact. We see this happening in some sense, in front of our own eyes. The fact that the universe was not the same in the past and that it has been changing. That we live in this aftermath of the Big Bang is just an observational fact. It's not a derived conclusion. What do I mean by that? What I mean is that because light travels at some speed, 300 kilometers per second, when we look at something that is very far away from us, light has taken a long time to get to us. So we're looking at something really in the past. So by studying things further and further away from us, we are looking at our universe at another moment, at an earlier time. And we can compare how the universe was before and after some time, and we can see that it has been changing. So the fact that we live in the aftermath of a Big Bang is not to be debated. We have pictures of the universe when it was this age, when it was this other age, and it's very clear. So let me give you some sense of some of the things that one can do when you realize that we live in this aftermath of this Big Bang. Of course, the question of why it's like this is another question that we can discuss in a little while. But so let me just give you some refresher of nuclei and atoms. So atoms, okay, have nuclei in the center, which are formed by protons and neutrons. Protons are positively charged, neutrons are negatively charged. And typically orbiting these nuclei, there are electrons which are negatively charged, making the whole thing neutral, an atom, okay? And so various atoms, the various names of the different elements depend on how many protons there are, and sometimes neutrons in the nuclei. Okay. The important point for the purpose of this talk is that we know what happens, so we can study these things in the laboratory. It's what everything is made of, and we can figure out, for example, if you bang together two atoms, if you bang them hard enough, the electron will come apart and will be on one part the electron and the nuclear on the other part. If you bang them even harder, you'll break the nucleus apart. Okay, and if you bang harder, you'll break the constituents of the nucleus apart and so on. But let me just stop at the level of the breaking the nucleus apart. Okay, so if you think of this expanding universe, the consequence of this expanding universe is that it's diluting because everything is moving away from each other. So if you go back, everything was closer to each other, and it also is the case that everything was moving faster with respect to each other. So when atoms in this universe were banging against each other, they were banging faster or harder in the past than they are banging later. So you can imagine what would happen. How would the history of the universe go? Let's just think about these things that we know about atoms and nucleus. And so if you go sufficiently back in time, you realize that the things are banging against each other so strongly that you will just break up all the atoms and all the nucleus, and so you will have the constituents of the nucleus, and by that I mean the protons and the neutrons separate and the electrons separate. And we also know that when electrons move around, they emit light, and protons also, charged particles, they emit light. So if you go back in time, you imagine that, or you realize that the universe should be filled with both protons and neutrons and electrons all together separated, and a lot of light all moving around banging against each other. Okay? Now the universe expands. What happens? It dilutes. So it's getting harder to find another proton to bang against, for example, if you're a proton, because everybody is further apart. Okay? And also we are moving slower with respect to one another. The universe is getting colder, so I haven't proved that for you, but it's true. And so what happened is that eventually you bang against other things not strong enough to break them apart. So the nucleus, which are the things that are bound stronger, will start to form. And when it bounces against another nucleus, it will not break apart. So roughly in the first few minutes, what you discover is that in the first few minutes, you will form some nucleus. So they will no longer be broken apart. And if you wait around 400,000 years, the things are banging against each other so weakly that even the electrons will survive and you form the atoms. So this is kind of a rough history of what you might expect happen in an expanding universe. And after this point in time, you also find that all the light that was there will no longer bounce against anybody else, and it will just move freely in the universe. So you expect there to see a lot of light left over from when the universe was hot and very dense. And it's coming from us from a time which is 400,000 years after the Big Bang. And now we know this. I wrote 400,000, but we really know it much more precisely than this. And indeed, this light left over from this very beginning was discovered here in New Jersey by Penzias and Wilson working in Bell Labs using this antenna. So we now can see this light from the very beginning, or in 1965 it was discovered. And what they discover is that you get more or less the same amount of light from every direction, just as you expect from this Big Bang model. And indeed, probably this was what sealed the Big Bang in the minds of the scientists at the time. And we now can measure this cosmic microwave background with great precision and its properties, and we are sure that it's coming from this Big Bang, from this earlier epoch in the Big Bang. So let me just keep this transparency. And just for knowing, if you want to carry some number with you, this light from the Big Bang, there's roughly 400, the light comes in particles that we call photons. There's like 400 of these photons in every cubic centimeter in the universe. So there's a lot of them, even in this room. It's in the microwaves today. That's why it's called cosmic microwave background. So the other typical example from these early times in cosmology is what's called Big Bang Nucleosynthesis, which is this time when, so the CMB comes from the time when atoms were made. The Big Bang Nucleosynthesis is the earlier time when nucleus or some nucleus were made. And this is just a plot. So you can just take nuclear physics from the laboratory that you can use for many other things, and you use it like bombs and reactors or whatever. So all that we know about nuclear physics, and you use it in the context of the expanding universe to see what happens, how these various nucleus would form in this expanding universe. And you discover that, so this is time, and this is the amounts of various elements. It doesn't really matter, but there's a line for hydrogen, a line for helium, a line for deuterium. What you need to take away from this plot is that if you trace these lines as a function of time, at the very early times there was just protons and neutrons, which are these two lines. Something happens around between 100 and 1,000 seconds in which all these lines, they go up and down and so on, which means that you are taking these protons and neutrons and forming these elements, helium, deuterium, beryllium. It doesn't matter which one, what they are, but they are various elements, light, what we call the light elements. They're all, take your textbook nuclear physics, if you want, do this, try to follow how various nucleus forms in our universe, and you realize that between 100 and 1,000 seconds after the Big Bang, a bunch of things form. And then you can go out with your telescope, look at the stars, and see if indeed the amounts that, so what this calculation gives you is how much of each you expect. So you go with your telescope, look at the stars, and see if you find these elements in the right amounts. And indeed, you do. So, so that's perhaps the other thing that totally nailed this notion that we live in the aftermath of this bang, of this Big Bang. Universe expanding, hot in the past, things forming, okay? So let's just focus on this plot on this side. The other one is maybe too complicated. But so if you imagine looking back, as you look back in time, as you look further away from you, what this is trying to illustrate is that as you look further away from you, you're really looking at other points in time, because light has taken some time to get to us. So if you can look sufficiently far away, you would be looking at the time of in which this the CMB, well, this is a little bit old, it says 300,000 years, we now think it's 400,000 years. I mean, cosmology has been moving so fast that we now know these numbers very precisely. Now, 5 years ago, we didn't know them. Anyway, so you can see, and I'll have better slides of this later, but just this illustrates two things, that when you look further away, it was a different epoch in the history of the universe, so different things were happening. I just talked about some of them, like this one and this one, but different things were happening, and we can actually either see some of them or see the remnants of some of them, so we clearly know what was happening, a minute after the Big Bang, 400,000 years after the Big Bang, then we see galaxies billion of years after the Big Bang. So. Okay, so so far I told you that I tried to tell you about the rough history of the universe implied by this expansion, dilution, and so on, this fact that we're living in the aftermath of this Big Bang. Now, the universe is not just boring thing made of only, atoms and so on. We know a lot of fun things happen in the universe. There's stars and planets, we're here, etc., etc. There's a lot of structure in the universe on scales much larger than atoms. So the atoms, for whatever reason, they form stars, which then shine. There are planets, people, dinosaurs, etc. So a lot of things in different scales happen in our universe, and this process is what it's typically called by us structure formation, the formation of structure. And we typically, so let me focus on things that are relatively big. You know about the stars, you know about the planets. Let's just discuss things that are even bigger than that you might not be so familiar with. So these are examples of things, pictures of, so these are real pictures of things in our universe. So by now, this discussion about these nebulae, what they are, we have beautiful pictures. We clearly see that there's a galaxy, gas, etc., etc. So these galaxies, so the smallest thing that I will discuss in this talk is a galaxy, which has 10 billion stars maybe. Depending. There's galaxies of every kind and various sizes, but I'm just some rather more or less big galaxy. So, and these galaxies are not just the biggest thing that there is. They do all kind of interesting things. Sometimes they collide. They live in big groups called clusters of galaxies. So here, what you see, all of these are a small fraction of the sky. where you see all of these galaxies that if you could take a picture in 3 dimensions, you would see that they live in some sort of spherical region called a cluster of galaxies, which can have 100,000 galaxies and so on. So there are structures bigger than galaxies, these clusters of galaxies, for example. This is another picture, a very famous picture called the Hubble Deep Field. So this is a part of the sky of the size of a dot. When you're reading a book, just the dot at the end of the line when you read at some normal distance. So it's a very tiny part of the sky. And there are, I think, a couple of thousand galaxies in this. Most of them very, very far away. And they were seen, this picture was taken by the Hubble Space Telescope. So there's a lot of interesting things in our universe. This is another example where what this shows is if you make a map of galaxies, in this case, it's just 2 wedges. Imagine putting your telescope like that and just looking at one wedge in one direction, some other wedge in the other direction. And you put a point for each galaxy. And this is distance in billions of light years. So this is very far away galaxies. So just to show you that the galaxies are doing interesting things. So they are not just a random distribution of points like thrown with no structure at all. They leave these regions empty that are called voids. There are all this filamentary structure that forms. These knots where these filaments cross, they are where these clusters of galaxies are. And so there's a lot of structure in this. And so this is the kind of thing that has been measured very precisely in the last decade or so, and from which we are trying to infer things about the beginning of the universe. And the other map that I wanted to show you is this map of the cosmic microwave background. This map was taken by a satellite called WMAP, which stands for Wilkinson Microwave Anisotropy Probe. And Wilkinson was a professor here at the physics department, I believe. So this is a map of this cosmic microwave background. And what this shows is, this light is coming from us, to us from when the universe was 400,000 years old. Just for comparison, the current age of the universe is like almost 14 billion years. So this is really very early, okay? We look at this and we don't see, it's not a universe filled with galaxies and the kind of things that I showed you in the previous 2 slides, which are more things in the more local universe. This is farther away, much further away, so it's much earlier times, and at this point there are no galaxies, there's nothing like that in the universe. This is a real picture, this is how some region of the universe actually looked like at this time. This satellite is still operating. It was launched something like 6 years ago, or maybe 7 years now. And what the different colors stand for is basically, it's a measurement of a measure of how much light you receive in the different directions, which or if you want, the temperature of the universe in various different spots in the sky. So this is just what that is. And what you discover, and that's why it took so long for these things to be discovered. They were discovered first by a previous satellite called COBE, is that these temperature differences from place to place were very small, like 10 parts per million. So at the 5th decimal place in the temperature, it changes from place to place. But for the most part, the temperature is 2.7 degrees Kelvin. Doesn't matter what that means, but some number. And it changes in the 5th decimal place from place to place. So it's very uniform. The universe at this age was incredibly uniform, very small differences from place to place. And somehow, those differences grew to form the galaxies, those clusters, those voids, those filaments, all of the things that we see. And inside of those galaxies, the stars, the planets, etc. So these are just 2 examples of how the universe looks at various times, just to impress on you the fact that we really have pictures of the universe when it was very different. So there's no question that we live in a changing universe in the aftermath of this Big Bang. And now we understand in quite some detail how you go from a universe that it's almost all the same with very tiny differences 400,000 years after the Big Bang, to a universe filled with the structures like the galaxy clusters and filaments that I mentioned to you. We have a pretty good idea how that happens, and it's because gravity is an attractive force. If you have in some region a little bit of excess of of matter, then the pull of gravity towards that spot is a little bit stronger, so more matter accumulates in this after a while, a little bit more matter accumulates in this spot, and so more you get even more pull towards this spot, and then it keeps growing, and it forms informs objects. So we understand that pretty accurately. So this is a little movie of, it's an animation produced by the WMAP team. And so just to give you a sense, I'll make it run twice. So it's the microwave background. You now go to one of these spots of the early universe and try to see how we imagine things happening. Okay, this is just an animation. It's not real data. But it shows two things. It shows how with time those tiny differences grow to form structure, and how by us looking we see this movie, if you want, in space, because when we look further and further away, we see things that were happening at different times. So this, if you want, is the movie in one spot, how it happens, these small differences, growing, filaments, stars lighting up, eventually having those filamentary structure, and how when we look from one particular spot, then we can see the whole movie, because when we look here, we see how the universe was when it was older. When we see further back, we see how the universe was in the past. So one more time. But this, although this is just an artist rendition, or however you want to call it, the real data is not so different from this. So let me just show you now compilation of the real data, and what you will see is galaxies. These galaxies are, or at least the locations of the galaxies in this movie, are real locations as measured by the Sloan Digital Sky Survey, a project with very heavy leadership also from Princeton University. So each point here is the location of a galaxy, and it will move around so that you can see how these galaxies this is really where they are. We've been put in this for the purpose of this movie. We are at the center, so now it spins around, so you can see this filamentary structure and voids. This is a real map of our universe. It's it's in some wedges. It's not fully filled, and this is because it's expensive to take pictures of the entire sky. So we do it in just some regions. It's not that the regions that we haven't looked are empty or anything like that, okay? So, and this is the microwave background. All of this is to scale, okay? So the microwave background coming from far away, the real picture from WMAP, again, also led by very heavy leadership by Princeton University, people in the physics department. So the actual map of that part of the universe, actual map of our more local universe as traced by galaxies, and there are also other objects used for the... So we see different objects. It's easier to see galaxies up to some distance, then we use other objects. It doesn't matter for the purpose of this talk, but this is just to give you a sense of the fact that we actually see all of this filamentary structure, we see the CMB, how it all fits together, just like this WMAP animation, okay? It's real, the real data looks very similar, and if you actually looked at the pictures, you see all of the galaxies in these little regions and so on. So let me just do it one more time. Let me finish one more time. So basically, no question, we live in the aftermath of a Big Bang, a universe that has developed a lot of structure, a lot of things in this universe. We now understand how it came to be. We see kind of how it started, some early times with the cosmic microwave background. With our computers and our pencils and papers and Mathematica, we can figure out how these things are supposed to evolve. We can compare with these observations, and we're in pretty good shape, I would say. So now, so this is what I've told you is the most solid part of cosmology, and I'm slowly trying to move backwards in time, and eventually I'll get to more speculative things. So okay, no doubt we live in the aftermath of the Big Bang. So what about the Bang itself? We really want to know about the Bang. Now that we know that we live in the aftermath of the Big Bang, we quickly lose patience and we don't really care about the details. We just want to know what happened before, okay? And there are some details that we are still have to work on it, things not quite working out, things like that. It's not perfect. It's not that our model is beautifully and there's just no potential problem. No, there are some issues and there's a lot of work but quickly you want to know what's more difficult to figure out, okay, or what's more, whatever. You see what I'm trying to say. So, okay, so what about the initial conditions? How did this Big Bang phase, this aftermath of the Big Bang phase started? Okay, we want to try to figure that out. Okay, and perhaps the hope is that by studying how this phase started, okay, we may learn something about the bang itself or whatever it made, whatever made this bang. That would be the hope. So I want to tell you a few facts about these initial conditions of this Big Bang phase, or after the Bang phase. By initial conditions, I just want to tell you about things about how this expanding phase need to have started in order for us to see what we see. Okay, so because we now have a very good idea of when things were created, when atoms were created, and so on. And how structure started, we can figure out how this Bang phase need to have started in order that it match our observations. So let me just tell you a few things about these initial conditions. And this again, this is not really anything that I'm going to say is now it's controversial or still speculative. So to now, all of that I'm going to say. At the moment, I'll let you know when I'm going into some more uncharted territory. And in any case, I'm going to give you the really conservative explanation. I'm not going to give you. So I'm going to take the party line of the more conservative people. Okay, which maybe I am one of them. So one thing that I told you is that okay, the universe is expanding. What does that mean? It means that. Everything is moving away from everything else, okay? But what I'll try to tell you, a little bit counterintuitive fact, is that in some sense the universe was much larger in the past than it is now. So let me try to explain this with some example, okay? So the example is the following. So imagine take two things, take two atoms, or take an atom that it's pretty far away from us, 10 million light years away from us now, okay? So this means that it takes light 10 million years to get from this atom to us, okay? Universe is expanding. Later on, it will be further away from us than even this distance. In the past, it was closer to us, okay? That's what it means. But so now let's look backwards and ask the question where this atom was. Let's say, now the atom is 10 million light years away. The age of the universe is 14 billion years. I told you 13.8, or I don't remember what I told you, but it's 13.8 billion years. Clearly, light can get from this atom to us. If this atom absorbs some light, we can tell because it only takes 10 million light years for it to get to us. So it's clearly, if this is in a star, it's a star that we can see now, okay? So let's ask the question where this thing was like a third of a second after the Big Bang. So we just trace it back, we calculate where it was, and it was much closer, of course, because everything is moving away from us. So in the past, it was closer to us. It was not 10 million light years. It was just half a light day away, pretty close. So in this sense, everything that we see was much closer to us. And so if we go back, that's the Big Bang, okay? But now look at these two numbers. This is a third of a second after the Big Bang. It was half a light day away, meaning light would take half a day to get from this atom to us, but the age of the universe is only a third of a second. So light did not have time to get from this atom to us. This is a perfectly nice atom that we can see now, but if we were there a third of a second after the Big Bang, it was something that it was further away than we can actually observe. Just as presumably we see all these galaxies in our universe, they continue, right? Nobody proposes that this ends like that. There probably are more galaxies and more stuff that we just don't see because they're so far away that light takes a long time to get to us. Okay, something that we see now was too far away in the past. That's the message that you should take away. It's indeed closer in centimeters, in light days, in feet. But compared to the distance that light could have traveled, it was much further away. So far away in this example that is like a separate universe from you, for all we care. At this time, this is an atom. If it was there, it was not there, you wouldn't care, okay? Because no information from this atom can get to you, okay? So in this sense, I want to say that the universe was much larger in the past, in that things that we can see today are very separated compared to the distance light can travel, okay? So just keep in mind this example, just if you get confused, I think this example is... So you can ask the question why this happens in this Big Bang model. Why is it the case that when you go back, eventually this time is not enough for you to see something that you can now see? And the reason is basically boils down that the gravity is attractive, so as you go back in time, not only things are closer to one another, but they're moving away from each other faster, okay? Or if you move forward, things are decelerating, okay? So, because gravity attracts everything else, so so we thought. If things are moving in some direction, there's some force between them, it slows down. So if you go back, it was moving faster because it's been slowing down, okay? So that's what is behind this. This is what is behind. The reason why this happens is that. And this leads to what's called the horizon problem. And so the easiest way to think about this is to look at this map of the cosmic microwave background, okay? And you look at two regions. So here's just some schematic thing. So we're here, we're looking in different regions. So one spot here, another spot somewhere else, okay? Now, this light that we are seeing comes from 400,000 years after the Big Bang. So light only, regions that were only like 400,000 light years from that point could have talked to this atom here that emits or the light that we see, okay? Turns out that if you look in the sky, two regions that are separated by more than a couple of degrees, so a few moons over, so the moon, 2 or 3 moons, you look at those spots that are like that separated, that distance at 400,000 years between those 2 points was larger than 400,000 light years. So those two regions had not had time to talk to one another, okay? And there are many, many of those regions in the sky, one here, one there, you're still filling the sky with regions separated like that, many, many of them, okay? So why? How come then how is it possible then that when we look at this region, the temperature of this universe at this time was pretty much the same as the one here, or here, or here, if they had not had time to, talk to one another and decide, let's be at this temperature. It's like if you were to look at your neighbor's, kitchen, and you saw 2 pans, and you look with your camera, you can figure out the temperature, and they were at the exact same temperature, and you wonder, how can this be? Well, there's usually a simple explanation. Even if they started at different temperature, you put them together, you leave them for a while, and they will come to the same temperature just by touching one another. But if you were looking at a movie and you saw this guy cooking, okay, and the thing was very hot, and then he put it on top of a very cold thing, and 1 second later, they were both of them at the same temperature, something would be weird, because in 1 second you know that a hot pan cannot become cold by touching a cold pan, okay? Same thing here. You see two things that are separated by in this case it's even worse because they don't even have time to even talk to each other, but how come getting to thermal equilibrium by communicating and saying, let's exchange some energy so that we are both at the same temperature, that doesn't work. They didn't have time to talk, okay? So how did that happen? So, one of the mysteries. And in some sense, you can think of all these different regions as, at the time we are observing them, as separated universes, because they didn't have time to talk. So in some sense, inside our own universe, there are all these many separated universes that we can observe, and we know they were separated. And so in some sense, when we say we observe our own universe, sometimes we have many different ones to study. Okay, so let me say one more other thing. So, So this point, this horizon problem, is probably something that it was very much in the mind of Alan Guth and the people inventing, what the theory of the bang itself that I will tell you a little bit about in the 80s, and probably it's something that you could have figured out, long time ago. It's not, or by long time ago I mean 80s or 70s or something. Now, in the last few years, we also know one more thing. And this is thanks to the WMAP satellite. We know that, so I told you that to form all of this structure, we know how this happens. You start with even if you start with some small differences, they grow and they form things, okay? But you need these small differences. Now, thanks to the WMAP satellite, we know that those differences were put in place during the bang itself, okay? They are there at the very beginning. They were not generated as the course of the evolution of the universe in the more normal phase. Okay, so this bang itself needs to do two things. It needs to take things that apparently could not have talked to one another and make them pretty much the same, so that the temperature of the CMB is pretty much the same, for example. But it also needs to make them not exactly the same, so that they start slightly different, so that eventually in one place a galaxy would form, in another place something will not form, or a galaxy of this type, galaxy of that other type. Okay, so it's a very strange situation. So those are the two things that are there at the beginning of the bang. And so now let's move to a little bit of more speculative stuff. So let's imagine that we want to make some kind of theory for the bang itself, or why things started this way. So what we know for a fact is that we live in the aftermath of a big bang. We know for a fact that there's all this structure. We know for a fact that this structure grows from small fluctuations. We know for a fact that these small fluctuations were created at the very beginning in some unknown period that I'm calling here the bang, okay? And we also know that the universe on regions that look very separated ends up being very much the same. So all of these are properties of this bang. So we're creating whatever came before this aftermath of the Big Bang, which we have so beautifully mapped and observed. So what is the leading explanation or model for how to create these conditions, right, for the universe to begin? What the theory for this bang, or the leading theory for this bang. And it's called cosmic inflation, and it was put, so this is, I put this picture up, I don't know for what reason, but just to put something. It's difficult to explain, so I'll just put a picture and tell you the people that have worked on it. So basically, that was the idea. So, but it was put forward by Alan Guth, who is a physicist at MIT. This is Paul Steinhardt, who's here at the physics department. And so if you see him at Small World or wherever you hang out in Princeton and you have a question about the Big Bang, so here is your guy. This is Andre Linde from Stanford. So these are, perhaps the people that are more recognized as the ones that have contributed the most to this set of ideas. And this is very much an active area, right? So it began in the 80s or so. So it's not. So the idea is. So what was the problem? Why? So when I told you when you went back, something that was 10 billion light years was now half a light day, but the age of the universe was a third of a second. I told you this happened because of the deceleration of the expansion, because of the fact that gravity was attractive, and so if you traced back something, it not only was was closer, but it was moving apart faster. And if you trace it back, in some sense, what is happening is that you go back in time. Things are moving faster until you hit the speed of light, and that's when the thing goes on the other side and you cannot see it anymore. So how can you make this? How can you get around this? Well, if you imagine that there's a period in which there was an accelerated expansion, meaning something in which two things were at the beginning moving not so fast, but then the universe, rather than gravity attracting everything, turn it into repulsion, so that something started with small velocities and then it grew to a very big velocity. You can take something that is very small, of which you can think that maybe thermal equilibrium or something made it all uniform, and stretch it to our entire universe. And this is a plot of the size of our universe versus time. We don't really know where this period of inflation is located in time. We don't really know if it's actually what solves the problem, but if it was, we at the moment don't really know where to put it. But just as a rough sketch, you can take a universe that's very small, and during this accelerated period of expansion, just make it into the big universe that we see today. That was the idea. And so for this to happen, you need somehow gravity to turn repulsive, and then the expanding universe, rather than be decelerating, being accelerating, meaning it's the velocities of things are larger and larger as a function of time. We now maybe not think of this, we cosmologists, we now have proof that this accelerated expansion indeed can happen, because it appears that our universe currently is undergoing such a phase of accelerated expansion, and we can measure this very accurately. We know this for a fact. So the universe, and if you fill it with the right substance, it can accelerate. So maybe if it was filled with the right substance in the past, it could have done this inflation period that could solve this horizon problem. But what about these small differences from place to place? And I think these small seeds of structure that then lead to the galaxies and all the structure that we see. And this is where I think the theory is the most beautiful, really. I'm trying to say in words, so, for all my physics colleagues, this is probably not, there's a lot of things that you would have complaints with, maybe, I don't know, but I'm trying to translate it into English. So this is my best attempt, okay? So there's this period of accelerated expansion, okay? Let's say you want to use this period of accelerated expansion to solve this horizon problem. The first thing that needs to happen, so you fill the universe with something, some substance, something that makes the universe accelerate. But there's one thing that you for sure know that has to happen, which is that this period has to end, because we don't live in that period. We live in this period of the aftermath of the Big Bang. So period of accelerated expansion, fine, but it has to end, okay? So this is uncontroversial. So this substance that fills the universe and makes the universe accelerate somehow is keeping time, okay? Because it needs to know at some point I need to stop and I need to let the universe do its normal thing, okay? So if you want to explain it this way, you need to fill the universe with a substance that can keep track of time, okay? So in some sense it's some clock, but the universe was very small at the time, so I don't remember if, sorry. So you can see this was Alan Guth's best attempt to do some numbers into this. This is very small size in meters, okay? Very small size. So we know that for very small things, the physics of very small things is governed by quantum mechanics. So it's not just regular mechanics that we know. But it's governed by quantum mechanics. And we know that in quantum mechanics there are certain things that you cannot do, or there are certain uncertainty principles, or there are certain... so one thing that you cannot do is if you have a very small clock, you cannot measure time perfectly accurately. And so in the inflationary theory, what happens is that you have this substance, it makes the universe accelerate, it tries to keep time to know I need to end inflation, but it's a small clock in some sense. The universe is very small, so it cannot keep track perfectly of time. And in different parts of the universe, the inflation ends at slightly different times. And those differences in the time of the end of inflation are, in the end, the small seeds that lead to structure. Why? Because if in one region the universe is still a little bit inflating, and in the other region it has stopped inflating and it's the regular universe, it will expand at a different rate, and it will get a little bit more diluted in one relative to the other, and that's how you make the initial fluctuation. So it's very nice marriage of cosmology and quantum mechanics. And in fact, one thing I learned from my colleagues here in the physics group when I arrived was that a lot of this was actually kind of already there in place in a lecture in 1939 by Dirac. So there's no time for me to read this, but I'm running a little bit late. But basically, one of the fathers of quantum mechanics, and in this lecture he pretty much asked the question, so how can the universe be so complicated? What could give rise to, if I don't want to put in the initial conditions the fact that here there will be a galaxy, here there will not be a galaxy, how can this be done? And he said it can be quantum mechanics, and in some sense a lot of it is spelled out there. And 1939 is a really early age. The expansion of the universe had only recently been discovered. Probably half of the astronomers did not believe that this was happening. And I don't know if half, I'm just making that number up. But the steady state version of the universe took a long time to die until probably the cosmic microwave background was found in 1965. So the models of the expanding universe were just starting to be developed. So we have some ideas of what could have happened in this bang. So, and we are trying to test those ideas. So what I want to spend the last 2 or 3 slides asking the question, okay, will we learn something more about this bang soon? Okay? So we know that we live in the aftermath of the Big Bang. We know how a lot of things happen, but the bang itself is the frontier. We just don't know how this happened. So will we learn something new soon? So let me tell you first the good news. So I think the good news is the fact that we now know that the structure that we see, these initial ripples, were put in place as a result of the bang itself, in whatever is this period of the bang, means that if we map the universe very precisely, if we make these nice maps of the cosmic microwave background, even better maps of how the galaxies are distributed, and from them try to infer these initial conditions, we are learning something about what was put in place at the bang. Okay, so there's a lot of measurements that we can do to try to get those initial conditions measured more precisely. And the other very good news is that our experimental colleagues are making very rapid progress. They are very smart, and they work very hard, and they're building experiments and telescopes that will probably characterize these initial conditions a factor of 10 or 100 better than we know them now in the next decade or so. So that's the good news. So this is just a collection of pictures of various instruments that are there, or all of these are there already, trying to measure the cosmic microwave background even better than we know it now. So people have gone to the South Pole. So they go to these experimental colleagues of us, they are tough. They go to the South Pole, they put their telescopes on balloons. And the other thing that is very exciting is that the next satellite to measure the cosmic microwave background, called the Planck Satellite, has already been launched. It's already taking data. This is a simulation of what this satellite will see, just to show something. This is actual data from some press release of that the satellite has already taken. So it's working, it's where it should be, everything seems fine. So we will know things about the initial conditions significantly better in the next 5 or 6 years. From the theory side, which are the things that people at the Institute do, mainly, so we are thinking about a lot of questions related to these initial seeds. How can we, how is these properties of the bang itself encoded in what we can observe, basically? And also questions about, is cosmic inflation something that can really happen within the theories, the physical laws that we think are applicable at the time when this happened? So all of these kind of questions are what are people at the Institute spend more, or some people at the Institute think about. So, of course, there are several caveats that we should keep in mind. First of all, even if we measure these initial conditions very accurately through these heroic efforts of our colleagues, there's no guarantee that there will be enough clues in this data for us to figure it out, okay? We may need to wait because there's just not enough information for us to figure it. Maybe there's too much freedom in our theories, in our understanding, to be pinned down by these observations or the numbers that we will get in the near future. We'll know things much better, but maybe that's not enough. We don't know. And in some sense, it's kind of quite different. I gave the example of Big Bang nucleosynthesis because that was an example in which we take laboratory physics, known, we make a bomb, we make a reactor. Everything is known. We apply it to the universe. We get something. We observe. It matches. Beautiful. Okay. Unfortunately, for the Bang itself, we don't have these physical laws that we already know from the laboratory. These processes happen at such high energies that we just don't have the power in our current laboratories to explore it. So we are extrapolating what we know by a big factor in energy, trying to see what could be the case at this very high energy. So we are in a very different regime. We are not just taking physics that we know and applied it to the universe, but we are trying to, in some sense, learn about physics that we don't exactly know by looking at the universe. It's a slightly different situation, which is not clear that we can make it as successful as in the case of, say, Big Bang nucleosynthesis, which there were no unknowns. There was all known from the laboratory. In any case, so this doesn't mean that we haven't made a lot of progress, even a lot of progress in the last decade or so, or 2 decades. A lot of these numbers that I told you, like the age of the universe, we didn't know so well even 10 years ago, or when I was in graduate school. I mean, definitely there has been a lot of progress in the last 20 years, especially about the understanding of the structure in the universe and how it came about. And hopefully the next 20 years, with all of these advances in experiments, will give us new clues and equal level of advance. And that's what we're all hoping for. And hopefully this will happen. So thank you. Thanks.
In your talk, you didn't mention the term dark energy. Does dark energy play a role in the accelerated expansion of the universe?
Yes. So I needed to hide a lot of things under the rug, okay? Because I needed to get to the beginning, okay? So let me just, for the benefit of everyone, say what this dark energy is. So if we measure the expansion of the universe now, indeed, I said something along those lines. We notice that the universe, the acceleration, the expansion of the universe is actually accelerating even now. The rate at which these things is happening now, how fast it takes for the universe, say, to double in size, is very different than in inflation. So most probably the physics of the two things, this accelerated expansion, are not related. However, we don't understand either of them at some level. So some people want to connect them. I'm not so hopeful that this connection will end up working out, but you can read papers trying to connect them. And this is some of the current acceleration of the universe, and the fact we usually talk about this by saying that the universe has to be filled up. This is just, in some sense, a rephrasing of the observation. The universe has to be filled up with some substance that makes it accelerated, and we've called the substance dark energy. But we've learned nothing. This was just names that we added, okay? It's just the universe is accelerating. And so I don't know if they are related. The conservative guess would be that they are not related, but at least they are related in the sense that it proves the point that the universe can accelerate. which is what we need for inflation.
Yeah, I've read somewhere that we know the number of atoms in the universe. Is that true?
Well, I would say it's fairly close to true, yeah. And by that I mean to within a few percent. So that's...
Let me ask from a simplified point of view.
Well, but so let me just say, these are... Maybe there's some atoms of some other kind that we have never discovered, but of the type that we know, hydrogen and helium mainly, this we know, because...
So then, if you know the number roughly, and if you condense those atoms and protons and neutrons down and down and down, so no space at all between them, would that be the origin of the universe before the Big Bang? I mean, what size would that be?
Well, okay, so a little bit of the question comes from maybe the slightly misleading way in which I said everybody was at the same spot in the same. You shouldn't think of the Big Bang as something that happened at one point in space and an explosion. And mainly the reason is that, so if you see a picture of an explosion, some atomic bomb going, there are certain things that were not part of the bomb itself, okay? And you see the blast going through some building. So all that we see was part of the bomb. So the way we think about it is so there's no sense in which there's some stuff that the bomb is passing by. So that's the reason why we think of it as a moment in time. Now, we also know that if we go back in time, even the atoms will have been broken into pieces, and the nuclei would have been broken into pieces. And so, in some sense, yes, this is what's happening. Everything was closer together in the past, but you still have the question as to, even if, let's just take your model, everything goes into, and then it starts. Why is it all moving outwards? It's still the question. Yeah, it's true, everything was closer together, but why did it start like an explosion in some sense? That's kind of the question that we're trying to answer. Yeah.
Is it as the Large Hadron Collider becomes operational, hopefully again this year? So if there is a detection of the Higgs boson particle, are the energies such that there could be some evidence of inflation? Or what do you expect?
No, I don't think. No, I think we will not get from there some direct evidence that we can link to the physics of inflation. I think for the purpose of astrophysics, the most interesting thing that could happen, or one of the interesting things that could happen out of the LHC is if they are able to identify the dark matter, which is something that I also hid under the rug. I told you we know everything about how structure forms, very nice, everything is very beautiful, we are in very good shape, you don't need to worry. Okay, for it to work, for the model to work, the universe needs to be filled with some particles, we call them dark matter, that we have not yet detected in the lab. Maybe it's not so surprising that we haven't detected them in the lab, and there are many experiments that are trying to do it, and probably in a few years we will have a better answer as to which particle this is. But that is, I think, the direction that it might be more advantageous for astronomy. Okay, if there are no more questions, thanks.